This is AP question number 4, FRQ number 4. So this one is one that kind of ties acids into everything. So I like that. Acids are difficult for people to understand exactly what they are. So this one kind of goes through the whole gamut of questions. And the topic is formic acid, okay, which is methanoic acid, which is what I believe ants use to sting with. So it starts by saying draw the Lewis structure out for formic acid. And that would just be simply a carboxylic acid like that. Okay, so you would have the carboxyl group with the alcohol group attached, and the combination of the two gives you an acidic effect. So this hydrogen bond is easy to remove the H plus from, and so that's very acidic, or somewhat acidic, depending on what your base is, I guess. So that's the first part, the Lewis structure for that. The second part says explain why this is then soluble in water. Okay, and I would address two kind of features, but when you're thinking about dissolving in water, you want to think size a little bit, and mostly you want to think about interactions. You want to think about what type of intermolecular forces. So for this one, you have the route you could go where you could talk about it being polar, because it definitely has the dipole here where you have the positively charged carbon and the negatively charged oxygen due to the electronegativity difference. It's also heightened by the fact you have another oxygen here pulling electron density even more away from the carbon. So you really kind of have a positive end of this and a negative end of this. And then secondary to that, this part of the acid is going to be very, very polar, so polar because it's going to be removing electron density from a hydrogen with no other valence electrons. So you have that exposed proton effect that leads to hydrogen bonding there. Okay. So you can talk about the polarity, you can talk about the hydrogen bonding. Both of those things will influence the solubility, but you also want to relate it back to the water. What's the water molecule going to do here? So the water molecule is going to bring its hydrogen end near this, or the oxygen end near this, or the hydrogen end near that, and that's going to be able to interact with all those different spots. And so this can be surrounded by water, which makes it highly soluble. Okay? So there is that element to it. There is also the fact that this is going to go on and it's going to react with the water, which is going to increase its solubility because this H plus can be removed to make that hydronium ion. Okay? Alright, so anywho, moving on to part C, it says that when this dissolves in water, it acts as a weak acid. Write out the reaction for that. So I'm going to write this as HCOOH plus water. Okay, so this is an acid-base reaction. This H plus is going to come from here to the water. Okay, this is going to be my base, this is going to be my acid. So when I'm done, I'm going to have HACU, and I'll have a hydronium ion, H3O plus. Okay? And then next part says, what's the Lewis structure of the conjugate base? So if this is my acid, the conjugate base is the same thing but missing an H plus ion. So Lewis structure is also going to be very similar, except it's not going to have the hydrogen attached to the second oxygen. And then really, because of that, we have a situation now where these two electrons can come down and form a double bond, kicking these out. So we actually will set up resonance structures where we would have this being the combination of the two, and the second one would be with a single bond on that oxygen. And I'm running a little low on room here, so I'm going to kind of make an odd bracket there to carve that off. Okay, so that would be the Lewis structure of the anion. The results is the conjugate base. And then in part 3, we're going to then look at those two things, and we're going to talk about what type of reaction an acid-base reaction is. So this is really getting into the Lewis realm here, where we're looking at electronically what happens in an acid-base reaction. So Lewis was a very, odd and not very friendly scientist. He was probably one of the smartest scientists never to win a Nobel Prize. But he was really, really, really good at going through what electrons do. That's why he has the credit for the Lewis structure, or it has the name of the Lewis structure. So he came up with the Lewis acid-base theory, and let's talk about that for a second here. So if we go through and we assign formal charges to every single thing on here. Okay, so the rule for formal charge is the bond splits one electron each. So the hydrogen gets one, the carbon gets one. Carbon gets one, carbon gets one, oxygen gets one, oxygen gets one. Carbon one, oxygen one. Then you look at what would the charge therefore be of that thing. Okay? So for this hydrogen, my formal charge is 0. I have one electron and I should. My carbon has 1, 2, 3, 4 electrons around it, as it should. So it would be no charge, no formal charge. And then the oxygen here is going to have 6 electrons around it, 2 from the bonds and then 4 from its pairs. This is also going to have 6 electrons, and this will have 1. So I have no formal charge on anything that's in there. But oxidation number is split differently. We don't split one of each of the electrons apiece. We put both to the more electronegative. So the hydrogen gets nothing. So it has a +1 oxidation number. The carbon will get the 2 electrons from the hydrogen because it's more electronegative, but it will lose the other ones to the oxygens. So the carbon actually ends up with only 2, and it should have 4, a +2 oxidation number. Okay, the oxygen is getting the 2 electrons from the carbon. This one is getting an electron from the carbon and 1 from the hydrogen, and the hydrogen gets nothing. So those would be my oxidation states. And then if we go through and assign it to the byproduct of this, if we assign it to the conjugate base, you'll see very similar things. The formal charge of the hydrogen will be 0, carbon will be 0, this oxygen is 0, and then this one will have a -1. Okay, and that's because that's now charged. And if we went and looked at the H3O+, that would have a positive formal charge on the oxygen. The oxidation numbers, hydrogen is still +1. The carbon, if you look, is still +2. This one is -2. And this one has 6 electrons, and it gets both of these for 8. 2 more than it should have, -2. So what's interesting about that is that the oxidation numbers don't change. What does that imply? That means that when I'm doing this acid-base reaction, there's no transfer of electrons. Most chemistry is dictated as being different from nuclear processes, as nucleus looks at the protons and the neutrons, and this looks at the electrons. So if there's no motion of electrons, what's actually happening? Because something happens in this. You can see color changes from indicators, you can see pH changes. So it turns out that some reactions are redox reactions, combustion, single replacement, and they involve transfer of electrons. And then some don't. So what do? Well, in this one, I'm moving a charged particle, but the charged particle is the proton. Okay, it's this H+. So this, being able to shift around is my reaction. In a precipitation reaction, there's no transfer of electrons, but there are transfers of ions. So as long as something charged is moving around. So part 4 says comment on whether this is a redox reaction. No, it's not a redox reaction. My oxidation states are constant, implying that there is no transfer of electrons in this process. Okay? So, and then part 4, part 5 says draw a hydrogen bond with the formic acid molecule. Okay, there are 3 options for this. You can put the hydrogen end of the water here. You can put the oxygen end by this here. And then also, you really can take the hydrogen end next to that oxygen. Now the reason why that works is because in this case, you're getting the key to a hydrogen bonding effect is to have that hydrogen bonded to something that's so polar and so small that it exposes a bare proton. So that's the proton exposed. After that, you just need something negatively charged to attract to it. So even though this is not bonded to a hydrogen here, this is something that will have a lot of negative charge and can therefore hydrogen bond with this hydrogen. Okay. Now I wouldn't be able to take this and bond it, have a hydrogen bonding effect with like a methane or something like that. It would have to have that exposed proton. This has the exposed proton, this has the exposed proton, and then I'm hooking that up with something that's negatively charged. So the oxygen in the water here is not the critical part. This is the critical part. This is what is exposing that proton by taking away its electrons so much so that it get that unusually high dipole moment that we call a hydrogen bonding effect. So that's most of the question. After that, it goes through and it says, explain why formic acid does not conduct electricity as long as it's in a pure solution, but that if you had it where in a dilute solution, it would conduct. So when you're doing AP tests, and they start to talk to you about conduction, it's really important to highlight 2 things. 1, you need charged particles to conduct electricity. Now in AP Chem, they want you to get ahead of the game in terms of electrons are no longer the only ones you're going to see. Okay? So in the past, you're used to seeing metals conduct electricity because they have free electrons. Now you want to add into the game ions. If you have a plasma, if you have a aqueous solution with a salt, if you have a molten salt, okay? All those things are going to conduct electricity because you have a charged particle, and that's going to carry that current. You're used to thinking of electrons moving down a wire as being electricity. But you can also have a cation moving through a solution, and that's electricity. The other key point, though, is they need to be mobile. Great question is, why does a solid salt not conduct electricity? Well, they're locked into place. So even though you have those charged particles, they're not moving. And so that inability to move, restricts your ability to conduct. So anytime you're talking about conduction, you want to be able to highlight those two things. But this also gets at another thing, acid-base. If you just have methanoic acid, HC-OH. We've taught you the whole time that acids are acids, but it turns out that's not an acid unless it has something with it that can act as a base. This by itself is just a chemical. So really, acids and bases is more of a process than a labeling of chemicals. Lots of things can be acids and bases that aren't traditionally thought of them, and sometimes things that are thought of as acids and bases can't be them. It's only when I hook a water molecule up to this that I can pull that H plus away. If I just have a bunch of these formic acid molecules, then I can't get rid of that H plus. I'm not an acid. Or formic acid is not an acid. So when I just have like a glacial acetic acid, where it's just acetic acid, or if I just have methanoic acid, it's very pure, then I'm not going to be able to transfer that H plus. Because of that, I don't have any charged particles that are free to move. As soon as I introduce the water, now I have my acid-base reaction. Okay? Now this H plus can come onto here, and I'll get my H3O plus, and I'll get my formate ion. And even though I won't get a lot of them because it's a weak acid, and it's not going to happen very much, the H3O plus is a stronger acid. Even though I don't get a lot of them, I will get enough particles that are charged and are able to move that I will now conduct electricity. Okay? And then the last part talks about why does this thing not work very well as an ideal gas. Okay, so really we're tying in as many topics as we can here. The question is, if you had this as a vapor, why would it not be very ideal? So ideal gas should bring it to PV equals nRT. And what you may not know is that is a physics equation. You can actually derive that from collisions and conservation of momentum and forces and come up with this on a per particle basis in one dimension and expand it to 3 dimensions and get this equation. And it's based on assumptions that physicists make. So in this one of the big assumptions is that when things bounce off each other, that it's an elastic collision. And in simple terms, that means that it's not sticky. Okay, in order for that equation to work, when the two gas molecules come together and collide, they may not stick together. If they do, then this is going to fall apart. The second assumption we make, and it's a little less important, is that all of these particles are points, meaning that they're so small that they don't take up enough volume to matter. If they are big, compared to the size of the container, then this equation starts to fall apart as well. Now, there's a correction for that, the van der Waals equation. But if we're going to use the ideal gas law, we want an ideal gas, we need these two things to matter. So the question is really saying, of these two, which is really being violated by this? Is it sticky, or is it too big? I don't think that's a very big molecule, so I'm not so concerned about number 2, but I am concerned about the stickiness. I have hydrogen bonding, I have a big dipole, and a small molecule that's going to allow those things to interact. When they're colliding, there's a very good chance that this is going to line up with another of the OH hydrogen bonding capable parts of another molecule. So I would think this would be very sticky, and I would see that I would have problems with that. In your van der Waals thing, that was the A corrective factor. The A value for this particular molecule should be very large, which will make it not work very well as an ideal gas. It'll behave much more realistic than that. If I wanted to minimize that, I would have to crank up the temperature so when they collide really fast, they don't get a chance to stick together. Or I would want to reduce the pressure by increasing the volume so that they're so far apart that there are fewer collisions between the molecules. Okay, and that would be it. If you come FRQ number 4, that would be all of the answers. And if you would like to see more, there are, of course, more as you scroll down, or if you click the links to the different sets of things.